Welcome back, guys, and today we're going to be getting into 7.4, which is double angle and half angle identities, and essentially we're just going to add to our arsenal of trig identities. And for the think/1pi, I've used a sum and difference identity on sine of 2 theta to come up with a new identity, and our hint is that sine of 2 theta equals sine of theta plus sine of theta. And so if we use one of our old identities from 7.3, that's a sum identity, and we know that would change into sine of theta, cosine of theta, plus cosine of the first angle, sine of the second angle. But since they're the same angle, this is really just 2 times the sine of theta, cosine of theta, right? Because sine times cosine and cosine times sine are the same thing, and we just have 2 of them. So that's really what we get for sine 2 of theta. And that's one of our new double angle identities, along with these cosines, which we get by doing the same thing, by doing a sum and difference identity on it. And then we get squareds with that one, which the reason we have so many more for cosine 2 of theta is that we get those by substituting in and out some Pythagorean identities. And then the tangent of 2 theta, also similar way, we get that one. And so for our first example, we have if sine of theta is 2/3 and theta has its terminal side in the first quadrant, find the exact value of each function. And I put our double angle identities over here just in case we need to reference them. And so we have sine of 2 theta. Well, we only have one thing for that, and that is the 2 times the sine of theta times the cosine of theta. One problem with that one is we don't have cosine of theta, but we do have sine of theta, so we can find it. So if we remember, we used it in our last unit too. If we move some stuff around from sine squared plus cosine squared equals 1, we'd get that cosine of theta equals the square root of 1 minus sine squared of theta. That's just from remember, sine squared plus cosine squared. If we minus the sine squared over and then take the square root of both sides, this is what we get. So that is 1 minus 2/3, right? Sine theta is 2/3 squared is going to be 4/9. You square the top and the bottom. And then that is the square root of 5 I'm getting ahead of myself, 5/9, right? Because 1 is 9/9 minus 4/9 is 5/9. And so square root of the top is just the square root of 5. We just leave that as is. Square root of the bottom, square root of 9 is 3. So we get that cosine of theta equals 5/3. Now, when writing this out, now we can do 2 times sine of theta, which is 2/3, times cosine of theta, which is the square root of 5 all over 3. 2 times 2 is 4, times the square root of 5 all over 9. None of that simplifies any further, so that is going to be what sine of 2 theta equals. So now we go down to cosine of 2 theta, and we're going to bring these with us, and we'll notice that we have a lot of options to choose from. You can pick any of them. I'm going to choose the bottom one just because we already have sine of theta, and sine of theta is probably the nicest number we have. So I have cosine of 2 theta equals 1 minus 2 sine squared of theta. And when I do that, I get 1 minus 2. Sine was 2/3 squared. 1 minus 2 times 2 squared is 4. 3 squared is 9. So then I get 1 minus 8/9, or 1/9. So that's what cosine of 2 theta would be in this case. Now, tangent of theta, again, let's bring this guy down with us. Tangent of 2 theta, Very similar thing, right? Except now we're going to need, since we have 2 tangent of theta all over 1 minus tangent squared of theta. Now we need tangent of theta, but it's a good thing that we know that tangent of theta equals sine over cosine, which is 2/3 over, and we found cosine to be the square root of 5 over 3. Dividing by a fraction is really multiplying by the reciprocal, right? So I'm going to ignore the bottom now. 3's cancel. We're left with 2 over the square root of 5. So times the square root of 5 all over the square root of 5 to rationalize. And we get 2 square roots of 5 all over 5. So let's use that. So then we get 2 times 2 square roots of 5 all over 5, replacing tangent of theta with what we found it to be, all over 1 minus 2 square roots of 5 all over 5 squared. So let's think about this for a second. We know 2 times 2 is going to be 4 square roots of 5 all over 5 all over 1 minus. All right, so squaring the top, 2 square roots of 5. So if I do 2 square roots of 5 squared or times it by itself, really this is all getting multiplied in any order. So we can do 2 times 2, which is 4, times the square root of 5 times the square root of 5 is 5. All right, so then we get 20. So that's 20 in the top. And then 5 squared is 25, which is really 1/5, right? So maybe I'll take a step down now. Don't want that stuff getting in the way. So we saw 4 square roots of 5 all over 5 all over 1 minus 4/5, right? This is 4/5. I might have said 1/5 on accident because I was already thinking ahead. 20 divided by 25 is the same thing as 4/5. So 1 minus 4/5 is 1/5. Again, dividing by a fraction is multiplying by the reciprocal. So ignore that. 5's cancel. We got 4 square roots of 5 divided by 1, or just 4 square roots of 5. And maybe I'll draw an arrow down here so we know what happened. And here is our answer for that one. Now, cosine, here first, let's bring this with us. Cosine of 4 theta, well, 4 theta is really 2 times 2 theta. So what we really have here is cosine of 2 theta. And so we kind of just have to modify our cosine identities just a little bit. Again, I'm probably just going to use the bottom one since I think the sine being 2/3 is the nicest thing we have. So let's go ahead and do that. So cosine of 2 theta is really going to be 1 minus 2 sine squared of theta, but instead of theta in here, we have 2 theta. So sine squared of 2 theta. Ooh. So here is where we need to go back up because we found sine squared, or we found sine of 2 theta to be 4 times the square root of 5 over 9. So this is really 4 times the square root of 5 all over 9 squared, right? Getting a little messy, but that's okay. 2 times 4 is 8, square roots of 5 over 9. So we really kind of end up with something a little complicated. Oh, I forgot to square it. Getting ahead of myself. So we have to square the top. So we have 1 minus 2 times, if we square this, that'll be 4 square roots of 5 all over 9 again. We can ignore this too. 4 times 4 is going to be 16. And then we're going to get square root of 5 times square root of 5, which is 5. So we're going to get 16 times 5, which is 80. And then 9 times 9 is 81, right? And then 2 times 80 is 160 over 81. And 1 would really be 81 over 81. So if we do 81 minus 160, we would get negative 79 over 81. Seems like a lot, but really it's just algebra, right? Just because it's fractions. Don't freak out. Just because it's a few steps, don't freak out. Just do your algebra, be diligent about it, and you will come out with the answer. So now moving on, here's our half angle identities, which we are going to use. And again, either write these down now, pause it, write it down, or if you have that sheet or already have it written down, that's totally fine as well. Moving over here, I had these ones over here too in case we need them. Use the half angle identity to find the exact value of each function. So here we have sine of 7 pi 12ths. And so we don't have a squared here, but we do have sine of theta over 2. And really, we can rewrite this sine as the sine of 7 pi all over 6 divided by 2, right? Because really you would multiply these denominators, so that would be 7 pi over 12. And now we have this theta over 2 thing where our theta is 7 pi 6, right? And so we can use this equation right here and recopy that down, except with 7 pi 6 where theta goes. So that's going to be plus or minus, really, plus or minus, the square root of 1 minus cosine of theta, which is 7 pi over 6, all divided by 2. Cosine of 7 pi 6 is negative square root 3 over 2. If you want to use your calculator, that's fine. Or, again, think of a reference angle, use your triangles. We have a bunch of ways to do it. We learned that in the beginning, so I'm not going to keep going over that. If you have questions on how you would get this without a calculator, please let me know, because that is core to pre-calculus. So we really have 1 plus the square root of 3 over 2, and 1 is the same as 2 over 2, right? So we can actually combine the tops there, and this is the square root of everything, plus or minus technically. And from there we get 2 square roots of 3, 2 square roots of 3, all over 2 divided by 2 is 4, or we would multiply them, and we have the square root of that whole thing, which really, that 4 on the bottom can come out as a 2. However, that top has to stay the square root of, oops, I accidentally combined those. This should be a plus. This should be a 2 plus square root of 3, right? I was getting ahead of myself. I combined denominators. So really, maybe I should write this previous step here, where we have the square root of 2 plus the square root of 3 all over 2 divided by 2, right? And that's how I get over 4, and there should be a plus here. So 2 plus the square root of 3. There we go. And so this right here would be our final answer. All right. Now, cosine of 67.5 degrees. We're going to use this one a little differently. Here, well, we're going to use it in the same way, right? We divided this by 2, so really we made this angle bigger here, right? We kind of doubled the angle that sits on top, because dividing by 6 is, half of what dividing by 12 is. So here we're going to do the same thing. Cosine of 76.5 degrees is the same as cosine of 135 all over 2 degrees, 135 degrees over 2. All right, same thing. So now we're going to, let me go snag our half angle identities. And now we're going to use the one for cosine. So we can just write, that's going to be the cosine of theta over 2, where our theta is now 135 degrees. It's going to be plus or minus the square root of 1 plus the cosine of 135 degrees all over 2. Oh, and up here, your final answer should be plus or minus because it didn't specify what quadrant we were in. And now, from here, it's just like the other one, just takes a little bit of simplifying. We have plus or minus the square root of 1 plus the cosine of 135 degrees. Again, you can do your reference angles and everything if you need to. Please ask me if you don't know how to do it, but that would just be negative square root 2 over 2 all over 2. We're going to do a similar thing here where 1 is really 2 over 2, right? So we're going to get 2 minus the square root of 2 all over 2, all divided by 2, and we're going to get a very similar thing where we get plus or minus the square root of 2 minus the square root of 2 all over 4, and then that 4 can come out as just a 2 on the bottom, and on the top we have the square root of 2 minus the square root of 2. All right, and so again, those are exact values right here that your calculator won't necessarily give you. It also probably wouldn't give you the plus or minus. So that's why these can be helpful, sometimes more so than a calculator. Now, for example 3, we have referred to this application here. Mike McDonald is an architect who designs water fountains. One part of his job is determining the placement of the water jets that shoot the water into the air to create arcs. These arcs are modeled by parabolic functions. When a stream of water is shot into the air with a velocity of v at an angle of theta, the horizontal model predicts that the water will travel a horizontal distance of d equals v squared over g sine 2 theta and reach a maximum height of h equals v squared over 2g times sine squared of theta, where g is the acceleration due to gravity. The ratio h of d helps to determine the total height and width of the fountain. Express h over d as a function of theta. And so our a here is exactly that. We are finding h over d and simplifying it. So let's do a first. Well, first off, h over d is going to equal h is v squared over 2g times sine squared. And you know what? I'm actually just going to write the sine squared on top. I think we should all be comfortable with, if times sine squared is on the outside, that might as well mean that sine squared is in the top here. All right, and now all over d Maybe I'm going to write this 2g in the middle so it looks nicer. All over d is going to be on the top of d is v squared, and again I'm just going to move that sine squared on top. Oops, and this should be the sine of 2 theta, not sine squared. Right, because h, oh no, h is sine squared, my bad. H is sine squared, I was right. H is sine squared. And then this one, d, should be 2 theta. Sine of 2 theta. H is 2g. Yeah, okay, I did that right. And this will be v squared all over g. And we know dividing by a fraction is really multiplying by the reciprocal. Oh, look at that. Once we ignore that, g cancels with g here, v squared cancels with v squared, and we're going to be left with sine squared of theta all over 2 times sine of 2 theta. Okay, well, now there's a couple more things we can do, right? Sine of 2 theta is really 2 sine of theta cosine theta, remember from earlier. So if I have 2 times the sine of theta cosine of theta, I really have 4 times the sine of theta times the cosine of theta. Oh, and hey, look at that. A sine cancels with a sine up here. And then we're left with sine of theta all over 4 times cosine of theta. And hey, we can make that even nicer. Sine over cosine is tangent, so really we can write this as 1/4 times tangent of theta, just so we write it in terms of 1 to make it nicer. Right? Maybe now we look at B. What is the ratio of the maximum height of the water horizontal distance it travels for an angle of 27 degrees? So now if we do B, really all it's telling us is that the angle it's shooting out of it is at 27 degrees. So we can put that into 1/4 times the tangent of 27 degrees. And you can just punch that into your calculator, and what we should get after punching that into your calculator is about 0.13. So that would be the ratio of the maximum height to the water to the horizontal distance it travels, 0.13. I'll circle that one as well. There we go. All right, one more. Our last one is some of our favorite ones, where we are verifying that cosine of 2 theta divided by 1 plus 2 plus sine of 2 theta equals cotangent of theta minus 1 all over cotangent of theta plus 1. Now this one is a little difficult, and I don't like the way the book shows it, because if I were me even, or you guys, I would not be thinking how the book did it. So I'm going to do it the way I would think, to show you how maybe more of a mathematician would think if they didn't have the most clear-cut way to the answer. Now, obviously, the book has a faster, maybe more clear way to the answer, but I think it's just a way that realistically you probably, or I even probably, would not come up with. And for the reason for that is because I see cosine of 2 theta and I see sine of 2 theta. Two things that we both know from our new identities, right? I'm not really looking at this when I see these nice identities I can use. The book does something to this right side, and I will do stuff to the right side, but not quite what we think. So the first thing I see is cosine of 2 theta and 1 plus sine of 2 theta. Now, actually, before I do anything to that left side, I think I'm actually going to rewrite that right side in terms of sine and cosine. So cotangent would be cosine over sine. Cosine all over sine. All right, and then if I made like terms here, I'd have to multiply this by sine over sine. So I'd get cosine minus sine all over sine theta, all divided by, and if I do the same thing here, I'm going to get sine over sine again. I'm going to have to multiply by sine over sine, but now I would get cosine of theta plus sine of theta all over sine theta. Multiplying by a fraction is really dividing by a fraction is really multiplying by the reciprocal. So not worrying about that. The signs cancel here, and we are left with, I'll rewrite the other side, cosine of 2 theta all over 1 plus sine of 2 theta equals cosine of theta minus sine of theta all over cosine of theta plus sine of theta. Seems like a lot, but we were just our first move was getting things in terms of sine and cosine and canceling. And the book keeps working a little weirdly with this side, but what I want us to focus on is this left side now. So everything's in terms of cosine and sine, and I'm going to first look at cosine of 2 theta. Now, when I first look at cosine of 2 theta, I want these two to end up matching, right? So I'm thinking, how can I get cosine of 2 theta to look like cosine theta minus sine theta maybe in the future, right? Thinking ahead. You might not be able to use one of these to get you there right away, but maybe ahead. Well, this top one really looks close, right? It just doesn't have the squares. This is introducing, this only has sines, this only has cosines, but this has them both. And I'm also thinking, hey, cosine squared minus sine squared, that's a difference of squares. I could get cosine plus sine times cosine minus sine. So I bet you something happens with that. So down here, I'm going to go with my cosine squared minus sine squared. And I'm just going to see if that gets me somewhere. Now, on the bottom, sine of 2 theta, we really only have one thing for it, right? And that's this. So let's just write that. 2 sine of theta cosine of theta. All right. And I think this way is still difficult, and I think you guys might still have trouble seeing it, but I think it would be better than the other way. So here we are. Okay. I just have such a strong suspicion in the top that I'm going to have to factor it right. That's the only way I'm going to end up getting a cosine theta minus sine theta is if that cancels. So this is a difference of squares. So the top, I'm going to change to cosine of theta plus sine of theta times cosine of theta minus sine of theta. And that's just from factoring, right? That's a difference of squares. A squared minus b squared equals a plus b, a minus b. Now, looking at the bottom, it might at first seem tricky, but here's where like thinking more like a mathematician would come in, right? So I know that I want to keep this cosine theta minus sine theta so I can match it up here, but I'm going to want to cancel this down here with something. How can we get this? Well, And I'm looking down here, and I see something that we have used before. The one thing I'm really noticing is 2 sine of theta cosine of theta. And something that's really popping in my head is another factoring identity, where if we have x squared plus y squared, or sorry, not x squared plus y squared, but x plus y together squared is x squared plus 2xy plus y squared, right? And I'm seeing 2xy right here. That's what's in my head. I'm seeing 2 times something times something, 2 times something times something. And we know something about 1. Isn't 1 sine squared plus cosine squared? Sine squared, sine, cosine. Maybe we're starting to see that a little bit. So let's replace 1 with sine squared plus cosine squared, but I'm going to write it like this. So sine squared, and then instead of adding cosine squared, I'm going to add it at the end, plus cosine squared, right? I really just replaced 1 with sine squared plus cosine squared, but now I did it in this order here. So I think maybe now we can see the pattern. Right? Now we could factor the bottom. Sorry, it takes a while to rewrite all of this. We can factor the bottom. That's going to be sine theta plus cosine of theta squared. Hey, that's going to cancel with one of those, right? It's really times itself twice. And then we really end up after those are canceled, showing that this is in fact an identity, because we can just rewrite cosine plus sine in the bottom over here to sine plus cosine, or vice versa. And hey, look at that, they're the same and they check out. I know that last one was a little crazy, but sometimes that's what I'm talking about when you just have to sit and think, and sometimes it requires a little bit of thinking ahead, and that's just one of these. But that will wrap up 7.4.